Let me first of all thank Isa for inviting me here, and I can see a lot of friends, particularly Dr. Mahajan, Dr. Dhareshwar, and many others whom I have met on various occasions. I had also earlier come to IFSA, given a talk here. IFSA activities are quite great, and I think we are getting late, so I will not talk about it just now. We'll continue later on. Women in science and technology have contributed a lot since centuries, I would say. But we have today even women not just contributing, but also are on the front in science and technology. Today, we are going to have this session on science and technology. I am very happy that we have 3 speakers right now. 2 are coming online, and without further delay, is the speaker. Okay, so our first speaker is Dr. Radha Bahukutumbi, and she is a distinguished scientist, laboratory for laser energetics, University of Rochester, USA. She will be online, and Dr. Madhu will first of all introduce Dr. Radha Mahakutumbi. So is she there online available?
I'm here if you can hear me.
Hello.
Can you hear me? I'm here.
Hello, Radha. Are you there?
Yes, I'm here. Can you hear me?
Oh, most welcome. Very good morning.
Good morning. Thank you for having me.
CV. Dr. Radha Bahukutumbi, a distinguished scientist, Laboratory for Laser Energetics, University of Rochester, USA. Her interests include understanding the physics of laser energy, coupling and growth of nanoformalities on implosion performance in direct drive implosions. Radha also enjoys identifying challenges related to nuclear astrophysics, and that can be addressed using high-power lasers. She came to LLE in 1997 after completing a PhD in theoretical nuclear physics at the California Institute of Technology to work on modeling of direct drive-related physics, including multi-dimensional hydrodynamics, codes, and particle transport in plasmas. Radha led direct drive research at the National Ignition Facility to study various aspects of direct drive until 2017. Prior to her current position, Radha led the Integrated Modeling Group and was chair of the High Performance Computing Group in LLE. She has served on several panels and committees reviewing inertial confinement fusion, including as an advisor to the Under Secretary of Energy for Science on the National Ignition Campaign. Radha also leads a group of women at LLE, Women in Science and Engineering at LLE, with the goal of hiring, mentoring, and retention. She received the Fusion Power Associate Leadership Award in 2021. Radha is a fellow of American Physical Society. Radha, it's your time. Please take over now.
Thank you very much. Thank you so much for introducing me. I'll share my screen. Can you see my screen?
Not yet.
Not yet. Okay. I'm sharing it right now again. Let's see.
Hello, ma'am. If you want, we can share because you have already sent the PPT.
Yes, but let me try one last time. If not,
Yeah, it's come.
it's come. Okay, excellent. So you can see it now?
Yes.
Oh, perfect. Thank you so much. Thank you very much for inviting me to speak at this conference. And thank you also for adjusting the schedule in the session. I really appreciate it. And thank you for the kind introduction. So what I thought I would do today is talk about what the prospects for fusion energy are through this process called inertial confinement. Now, fusion energy has significant advantages over any source of energy that we have today. It's relatively carbon-free. It's called base load, which means it can operate 24/7. It's clean. It's relatively pollution-free. And there is no danger of a meltdown. It doesn't require large land footprint. So you can actually place it near population centers. So there are all these huge advantages for fusion energy. But the flip side of it is that it hasn't been realized yet. And so I will talk about all the efforts that are going towards realizing fusion, exploiting what's called inertial confinement fusion to get to a fusion power plant. So what I show here is a schematic. Can you see my cursor? No?
Yes, please. Yes.
Okay. So I show a schematic of what a power plant might potentially look like, right? So there's something called a target chamber, which is where all the physics takes place and that we need to address. In a traditional power plant like coal or nuclear or coal or natural gas, what you would do is just burn the stuff in here, and then you collect the heat and you convert it to steam, which in turn turns turbines, which goes to the grid and so on. What's different between a traditional power plant and what's called a fusion power plant is what's happening on the inside here. And that's the work that has been taking place over the last nearly 50 years or more in trying to realize. So instead of burning something, what you have here are implosions, which are driven by lasers. And what is results are fusion reactions because each capsule which implodes is filled with isotopes of hydrogen called deuterium or tritium. And that implodes, producing fusion reactions. The heat or the energetic particles that are produced from fusion reactions are then used to generate heat, which in turn creates steam, turns turbines, and goes to a power plant. So this part stays the same. It's what's happening inside here that is all different. And notice that I mentioned lasers, I mentioned implosions, I mentioned tritium. So I'll talk a bit more about all of that. So inertial fusion energy has the potential to provide baseload 24/7 power near population centers and with little pollution or radioactive waste. And so that makes it extremely attractive. But three aspects need to be integrated for fusion power plants to contribute significantly to the energy landscape. One is to establish the scientific framework. And the science hasn't been fully resolved yet, but most recently, that is on December 5th of 2022, just 6 months ago, we demonstrated extremely high fusion yield at what's called the National Ignition Facility. This is located in California and in the USA. And it has demonstrated proof of principle, which is needed for all fusion approaches. So there are many ways of doing those implosions. And we demonstrated for the first time this proof of principle that it's possible to get something called gain out of an implosion. But to go from there to a power plant is a long road, and that's part of my talk. And the second part is the technology and engineering developments, which need to happen at scale. That means at the scale of a power plant. And this work is just beginning. So work is now beginning on the choice of appropriate driver. So what's the driver? A driver is something like a laser. What form of a laser? How much energy and so on. So an appropriate driver. I mentioned capsules. Those are the targets. I mentioned tritium. Where do you get the tritium from? So you have to breed it. And how do you diagnose what's going on? Because you obviously have to start with some challenges when you start a power plant. So diagnostics, etc. But work is just beginning on all of that with the goal of an eventual demonstration of a power plant. And then I'm not going to talk about the last part, which is all the policy and legislation and tax policy and so on, right? The ultimate power plant has to be comparable in cost to alternate energy sources, which means that you have to have regulations, tax benefits, and things like that. I won't talk about all of that, but I'll talk about these two related to the science and technology. So fusion reactions require very high temperatures. So what I show here is what's called a reaction rate, which is the probability of a reaction taking place versus the temperature that's needed. And I mentioned DT, deuterium, tritium. And the reason we speak about those in the fusion world is because it has the highest probability of reaction compared to many other reactions that take place at the kinds of temperatures that we can achieve in these implosions that I spoke about. So we can achieve temperatures of about 20 keV or 30 keV or so. And in those, the highest probability of fusion reactions taking place is deuterium and tritium. So for example, 10 keV that I talk about here is 120 million degrees, which is 10 times hotter than the interior of the sun. So these are the kinds of temperatures that we have achieved in the experiments that I spoke about at the National Ignition Facility. So clearly we are forced to deal with deuterium and tritium. And the reason I say forced is because tritium is radioactive. It has a half-life, very short half-life of only about 12 years or so. Nevertheless, it's not found in nature. So you have to find a way of getting tritium. Deuterium is abundant in nature. It's a huge portion of the oceans, so it's very easy to get. So somehow we need to get tritium for a fusion power plant to work. Now, the motivation for all of this is, of course, the sun, right? So here's a picture of the sun taken by the Solar Dynamics Lab, which is a branch of NASA. So stars emit light and heat from fusion reactions. So we're talking about very, very hot cores. But the hot plasma is confined by the gravity of the sun. Now, anything hot likes to expand. And it's the gravity of the sun that's holding the hot plasma in place and allowing these fusion reactions to take place. Now, how do we achieve that? I mentioned that we get 120 million degrees here on the Earth, but we need to confine that somehow. And so there are three credible approaches to high fusion yields, and a high is in quotes because it's relative. And I'll explain what that means in the context of a fusion power plant. Within the laboratory, using what's called inertial confinement. So the sun has gravitational confinement. Here on Earth, we use, I'll talk only about inertial confinement. There's another way of doing it, which is using magnetic fields. India is very active in the magnetic field world, contributing to the huge enterprise in France called ITER. And there are many labs in India that work on that. But instead, I will talk about inertial confinement. So there are three ways of doing it that we are studying here in the US and also others elsewhere in the world. What I will focus on are these two because these are purely laser-driven approaches. The first one is called laser indirect drive, and the second is called laser direct drive. So in laser indirect drive, you have this capsule, which is made of gold, and it's called a hologram. And what you do is you shine these lasers on the walls of this hologram. It generates X-rays. The X-rays then implode this capsule, which is there in the center, generating the very high densities and temperatures that I mentioned. That's indirect drive. So indirectly, you're heating the capsule. Direct drive, you shine the laser directly on this capsule. And then the physics is the same, which I'll talk about in the next slide, as the laser indirect drive. So it's basically the difference in the drives that makes the difference in the two names. So there are different lead laboratories studying this. The indirect drive is studied by the Los Alamos National Laboratory and Lawrence Livermore National Laboratory and us. And they have a huge facility called the National Ignition Facility in Livermore, California. Direct drive is primarily studied by us at the University of Rochester, and we have a laser facility called Omega, the Omega lasers. So here's a schematic of what these two lasers look like. This is absolutely not to scale because this is the size of many football fields. This is about the size of less than a football field. So this is huge compared to this particular facility here. So the Omega laser, which is the laser we have at the University of Rochester, is a very, very high intensity, high power laser. It's about 30 kilojoules or so. The NIF is significantly larger, the NIF meaning the National Ignition Facility. It's about 30 times or so larger than the Omega laser. So so what you see here is the typical approach. You start out with a single laser, which is centered here, which is of the scale of millijoules, and then it's split into many different nominally identical beams, and it's also amplified in energy. So ultimately, you have 60 beams, which are on the vertices of a soccer ball, which is incident on a small pellet, a millimeter-sized pellet, inside this almost 1 meter-sized target chamber here. So you have beams which are ultimately incident on this millimeter-sized pellet. So this is like almost the scale of one football field. So you can see the precision that's needed in generating these nominally identical beams, and the precision that's needed in directing it onto a millimeter-sized target, and the precision that's needed in terms of positioning this target inside this massive target chamber. The NIF follows very, very similar technology, except that the beams are arranged differently. So they are arranged on an axisymmetric way. So the red here are the beams, which is arranged in the center of this target. Now, this target chamber is about of the order of 15 meters. So you have a few millimeter-sized targets which are placed inside this target chamber of the order of 15 meters. And you have this 192 beams here. Here you have 60 beams, here you have 192 beams, which are incident on this pellet. So that's shown here. So for direct drive, you have this capsule and the beams are directly incident on the pellet, whereas the 192 beams in the NIF are incident on the walls of a gold hole drum, which generates X-rays, which then implodes the capsule to generate those high temperatures that you need. So the aim is to drive these implosions to develop conditions for a robust hotspot and propagating burn. So what does that mean? So here's the pellet, right? So it's out of 4 millimeters on the NIF. So you have whatever it is, X-rays or the laser, which is directly incident on the pellet. So I'm describing what happens inside that target chamber when the X-rays hit the gold wall and hit the pellet, or when the lasers directly hit the pellet. So what happens is when the driving driver, which is either X-rays or directly the laser hits the pellet, material ablates off this pellet. And then because of Newton's laws, it sends in a shell, which is literally like a rocket. So you can use the equations of a rocket to describe the implosion of the shell. Once the shell implodes, the kinetic energy of the shell is converted into a temperature of the hotspot, which generates very high temperatures and fusion neutrons. Alphas. So here you have the D and T reaction producing neutrons and these alpha particles, which are basically helium ions. These helium ions propagate through the target, the high density region, and deposit their energy, in turn raising the temperature. And then again, fusion reactions take place, which again produces more helium, and which in turn propagates through and raises the temperature. So as a result of which, you have this burn wave that goes out into the target, and it produces very high number of neutrons. So what's shown here is the kinds of conditions that you generate. You generate temperatures of the order of tens of keVs, which is about 100 million or 120 million degrees or so, and surrounded by very, very cold, very high density shells. So this is almost 1400 grams per cc, which is about more than 2000 times the density of the solid deuterium tritium shell that you started out with. So you have very dense, very hot plasmas generated here. Now, ignition and gain is what we are interested in. So gain is the fusion energy that's produced, which is about 17 MeV or so for this particular reaction, divided by the energy of the laser. So it's ignition is the process in which the alpha particles are stopped in the hotspot and produce more fusion reactions. Gain is when this fusion reactions propagate out into the cold shell and produce more and more neutrons, such that you have some ratio here. So indirect drive, which is what takes place in the National Ignition Facility, which is the facility meant to study that type of physics, has recently demonstrated gain greater than 1. So this is what I mentioned in my title slide. The indirect drive, I remind you, is this whole drum that you heat and then you drive it with X-rays and implode this capsule. And that was an effort of nearly many decades in the making. It started in the 1970s with the Shiva laser, and then the Nova laser in the 80s, and the National Ignition Facility was built in the 90s. And finally, in 2022, in December, we generated gain greater than 1.5. We generated 50% more energy in the fusion products than what was incident by the laser. So the history is shown here over the last decade or so. It started out as very small, and then, systematic changes to the science, understanding of the science, fixing the technology better and better, and things like 3D printing, understanding, diagnosing better what's going on, and so on, brought us to this point here. So this was a huge achievement, which if you go to YouTube, you'll see a lot of videos on this. And basically it sets the stage for us to try and understand how we can get gains higher than this, which is what is needed for a power plant. So here's a schematic of a power plant. So here's a driver, which is the laser. And I told you this implodes this target. So driver has some efficiency. It's a function of, there's some energy which is incident on the driver, and based on this, the efficiency generates about the energy of the laser. So on the NIF, it took about 400 megajoules to produce about 2 megajoules of energy for the laser. So that means eta D is much less than 1. So it's 2 divided by 400, right? Eta D is much less than 1. And then it ultimately produced a gain of 1.5. So this is what the proof of principle was about. The rest is the same as what takes place currently in power plants today, right? So then you have fusion energy, which is gain times the energy of the driver. And that goes into driving the turbines with some efficiency, and that goes to the grid. And then some of that energy has to go back to drive the driver, right? And then for fusion energy, you have to do this at the rate of approximately 10 per second, 10 hertz. So you have to take these implosions, drop them into the target chamber, implode them, and you need an eta D of gain of greater than 10. Remember, eta D, I said, was much less than 1 on the NIF, which means you need very, very high gains to actually have a reasonable power plant. Instead, what you could do is to design new drivers, and there are many in the offing. People are now starting to study solid-state drivers, which can get you gains of the order of 20%, excimer lasers, heavy ions, all of those can get in the 20% range or so. If you can do that, then eta DG greater than 10 implies that gain has to be about 100 or so. So we need to go from gain of 1.5 to demonstrating a gain of about 100 or so, along with trying to improve the driver efficiency with these new drivers to get to a fusion power plant. So the first step is, of course, to go from gain 1.5 to a gain of 100. And there are many things that we study we've studied historically in order to get to this point of gain of 1.5. You have to, as I said, you have to place this target precisely at the target chamber center. You cannot have too old a target because tritium is radioactive, it undergoes beta decay. So even a few days can significantly impact the performance of the implosion. The targets have to be clean. I show you an example of targets with lots of defects. And then there are finite size laser beams. Each laser beam has a speckle non-uniformity on it, which can ruin the implosion. And then there are other sorts of physics, which is the interaction of the laser with the plasma outside the target that's ablated off. Historically, this is what has driven ICF laser development. And this is what is important for us going forward to determine what the parameters of the laser need to be. So we are working on all of this to increase the gain. But the advantage of IFP over all the other approaches that people are studying, like magnetic fusion energy, is that it's modular. And you can also test different concepts using the same driver. So here I show again a simple schematic of a power plant. So this, as I mentioned, this is where all the action takes place. At 10 hertz or 10 per second, you have to inject these targets into this target chamber. You have to fire these targets, result in an implosion, enough neutrons. These neutrons will then interact with what's called a blanket here. And the blanket is made of lithium, and that produces heat. And then you can use that heat to, using a heat exchanger to produce steam, turbines, electricity, and so on. So the first thing is, of course, to get the gain up. The second thing is to learn how to inject these targets at 10 hertz. But remember, I also said we need tritium. So somehow lithium, and so we need to extract the tritium that's produced by the interaction of neutrons with lithium also. So lithium serves two purposes here. So if you can extract those tritium and use that to fill the targets and then send it back in here, that would be a self-sustaining nuclear power plant. The beauty of it all is these pieces can be studied independently. So we can study the physics right now. A different group is studying tritium breeding. A third group is studying how to generate these high power lasers using the repetition rates of 10 per second and so on. So it's very modular, unlike magnetic fusion, where everything is tied and coupled into the design of your device. So here you can study target design, targets, drivers, fuel cycle means tritium. You can build the diagnostics, you can perform experiments and so on. So you can do all these time. So base load operation, as I mentioned, which is 24/7 operation of an inertial fusion energy plant, requires rep-rated operation. So small power plants is what people are trying to target, 100 to 300 megawatt electrical. They require operating at about 10 hertz with a gain of about 100.
Hello?
So yeah?
Can you hear me? No?
Yes, I can hear you. This is my last slide.
Yeah. Okay.
Yeah, Yeah. So technology development and engineering opportunities are there for identifying reparator drivers. You need to mass manufacture these targets and make sure they're clean. You need to breathe tritium. You need to inject targets into the chamber. And you need to clear the chamber of all the debris before the laser shoots again. And then, of course, there are high temperatures. So there are X-rays. And so the wall of the chamber can be sensitive to all of that. So a lot of people are doing research in all these approaches. So I'll summarize here and say inertial fusion energy has the potential to provide baseload power near population centers with little pollution or radioactive waste. And we have demonstrated the proof of principle science that's needed for inertial fusion energy. And a lot of technological engineering developments are beginning in different parts of the US and really all around the world in the context of inertial fusion energy. With that, I will stop and take questions. Thank you.
Thank you, Radha, for a wonderful talk, taking us into the fusion reactor. And we welcome some questions. Yeah, please.
Hello, Dr. Radha.
Yeah,
Thank you
hi.
for this presentation. I am Shyamla Bharadwaj, and I just wanted to know which are the laboratories which have achieved break-even condition until today. Is there any laboratory which has achieved the break-even condition for fusion?
Okay, so there are different definitions for what break-even is, right? So what I spoke about was scientific gain. So that's only the laser energy, the denominator, right? It's not the energy that came from the electrical grid to power the laser. It doesn't take all that into account. So if you talk about scientific gain, there's only one laboratory that has achieved that. And that's the Lawrence Livermore National Laboratory, the laboratory that I work with. And Livermore, California. That's the only laboratory that have shown scientific gain. But if you take into account all the efficiencies from the power plant and so on and so forth, there is absolutely no laboratory that has demonstrated that yet.
Yeah, thank you. So we have a long way to go.
We have a long way to go, absolutely.
Yeah, Dr. Radha, it was a wonderful presentation on the internal inertial confinement fusion. You have said ITER is already on the, being established. I think I should turn this side, yeah.
Yeah.
But I would like to know, like already Shyamla had asked, when would you see a fusion reactor based on inertial confinement?
So there are a lot of challenges, right? Because first we have to resolve the science. And then also the engineering has to develop. And that's true even of magnetic fusion. They need to resolve the science and the technology needs to come about. There are some commonalities between the two, so we are starting to work together. So it's hard to establish a timeline for fusion energy. I mean, clearly people have been working on it since the 1970s. We've just had a physics breakthrough. So I'm not going to put any timeline on it. Let me just say, I would be extremely happy if I saw a fusion power plant in operation by the end of my lifetime.
Yes. Radha, this is Lalita Dhareshwar.
Hi, Lalita, how are you?
I was involved with this kind of work in BARC, of course, on a very minuscule scale, but I had a good opportunity of visiting NIF way back years ago. Yeah.
I see.
Yeah, but I could not visit your Rochester lab. But what I would like to ask you is, in the direct drive scheme, the requirements are so stringent for uniform illumination. Like even 1% non-uniformity can just break up the pellet. So why is it that Rochester is focusing on direct drive when it is easier to get uniformity using the hall room targets and X-ray driven? So I just wanted to know that reason.
So there are pros and cons for each approach. For indirect drive, the advantage is that it is not so sensitive to the individual beam speckle of each laser beam. But it is sensitive to long wavelengths because there are a finite number of beams that are incident on the whole round wall. So it can be asymmetric, and that's one of the challenges that we have had to control. So there are different long wavelengths that these two schemes are sensitive to. But the flip side of indirect drive is that it's not very energy efficient because you lose a lot of energy in generating the X-rays, and then the X-rays have to drive the whole round. So the advantage of direct drive is that it's very energy efficient. So it can actually absorb about 4 to 6 times more energy into the capsule from the laser than indirect drive can. And so that means that it places it's the requirement on the lasers energy that's needed is much weaker for direct drive than it is for indirect drive. And that's a huge advantage.
Yes.
And there are ways of making the laser beam smooth. That's what Rochester has invented historically.
That's really great. And other question I wanted to ask you was, I have come across many schemes for the target, structuring the target for
Right.
overcoming many of these problems. So have you been doing that many, I mean, instead of having a single wall target to multiple shells and things like that?
Yes. Right.
Okay.
Yeah. So there is work that takes place on that at LLE, where University of Rochester, where I am. Los Alamos National Lab is also pursuing that. There are also other schemes that are being pursued by other, Livermore pursues some of those schemes. Japan is very big on one of those schemes. So there are other schemes, other target types that are being pursued by other labs, including ours. But for the purposes of this talk, I sort of limited myself to that.
Thank you so much. I hope I have an opportunity to visit your lab.
Yes, absolutely. You're welcome.
Thank you.
So thank you very much, Radha, for a nice presentation and discussions we had. Unfortunately, we do not have more time to have further questions, although I'm sure that there are many scientists here who want to ask more questions, but sorry about that.
Oh, no problem.
Because next speaker is waiting now. So thank you very much and see you again.
Thank you. Bye-bye.
Sure.
Hello, just pay attention, the poster girls. Those who have put up their posters today, just go and take care because due to the wind, they are falling out. Please. Yes.
No. We'll have the, excuse me. Okay. Okay. So let us proceed to the next talk that is by Miss Keerti Rane, Director Level Principal Laser Program Manager, Microsoft, Seattle, USA. She will be talking on challenges faced by women in the software industry. First of all, I will ask Dr. Madhu to give her brief introduction, which will be followed by the talk.
Thank you, madam. Hello, Dr. Keerti Rane, Principal Lead Program Manager, Microsoft USA. She is responsible for Microsoft's commerce, billing, and tax platform. She delivers tax compliances and billing features through requirements gathering, prioritization, project management, software design, and technical problem solving. In her various capacities at Microsoft, for the last 20 years, she has worked on multi-tiered and distributed system architecture of billing, tax, financial systems platform, written in C/ and running an Azure infrastructure. She is also the subject matter expert in commerce system, architecture, billing user scenarios of Azure consumption, reservations, and 0365 offerings, revenue recognition, and tax calculation. She has earlier worked at ILX System as senior developer and senior programmer, where she wrote real-time stock exchange feed, parsers, and business rules. She was also the subject matter expert in NASDAQ Level 2, futures, options, and future options and specialized in C and C++. Dr. Keerti received her graduation degree of BE Computer Science from Gokte Institute of Technology, Belgaum, India, and did her MS in Computer Science from Clemson University, South Carolina, USA. She is the founding member and facilitator of Male Allies Program, mentoring programs, and women's networking hours for Microsoft, and certified allyship facilitator, delivering courses for employees across Microsoft. Hello, I hope Keerti, you are there.
Hello, yes, I'm here. Can you hear me?
Hello,
Hello.
Kirti, please
Hey.
start sharing your slides.
I will do that. Can you see my slides? Let me know when you can.
Yeah, okay, yes.
Awesome. Thank you so much for that introduction. Thank you for inviting me to come speak at this conference. Many, many thanks to IUSA for inviting me, as well as especially Dr. Mahajan, Dr. Bharadwaj for partnering with me on getting this presentation ready. And just super thank you to Dr. Radha for that brilliant talk recently. So we're switching gears now to talk about challenges faced by women in the software industry. As the introduction said, I have been working at Microsoft for 20 years and have been a woman in technology for quite a while. I worked for 10 years prior to Microsoft doing software programming. At Microsoft, I've done testing as well as program management. I run the billing and tax platform at Microsoft right now, and I love solving really hard software technical problems. In my background, as mentioned, I currently work at Microsoft. I've done a lot of diversity and inclusion work at Microsoft. So I run the Male Allies community. I founded this community. I also started getting women together to talk about the challenges that they face working in technology, because it's unfortunately still today a very, very male driven community. And I also provide mentoring for very early in career women, because as they join the workforce, it's important to give them the support, the advocacy, the sponsorship that they need so that they can be successful in their careers, just as some of us have already done so. I'm going to move to the next slide very quickly. So I wanted to talk a little bit about gender bias and unconscious bias, because it still exists in the software industry. This is switching gears from the very, very technical discussion from earlier. But for those of us who work in the technical industry, it's important to understand some of the challenges that women face so that we can understand how to overcome them and still be successful, as some of us have been able to do so. And I like this cartoon here, which talks about, what's the difference between being assertive and being aggressive. The only difference is your gender. And the thing I want to highlight with this little cartoon, with a little bit of humor here for a very, very serious topic, is that when a woman can be assertive at the workplace, can talk very confidently about things, she might be viewed as being aggressive. Whereas when a man is, talking about things with a lot of confidence, a man can be seen as a leader. And what they're saying is actually the same, but just because of the gender, they're being treated differently. And this can get in the way of people's careers and their career growth. So just a little bit of time we'll spend today talking about what these challenges are. I do want to call out one caveat, is a lot of the challenges that we face, the gender bias that exists, is because of unconscious bias. It is not malicious, it is not intentional. And mostly it happens because of social programming or what the media is putting out there. And what we are trying to do, in this industry is try to raise awareness and help get more allies from the senior male leaders that we have around us who can help, dispel some of these myths and still continue to support the women and make sure that women are successful. So some of the examples of the challenges I'd like to talk about today are, number one, women get interrupted or ignored in meetings. And as a result of this, women may not be heard. So you may be solving a really hard technical problem, but if you're not able to be heard, then your career may not grow, or you may not feel fulfilled in your daily activities because it's so hard to just have your voice be heard. Some examples that I can provide are, I was talking to a colleague the other day, and she said she was in a meeting, somebody was sitting across from her and asking her questions about a really hard technical problem. She provided a solution. She had a proposal. She had exactly, from her subject matter expertise, she knew exactly how to solve the problem, and she talked about how to solve the problem. The person sitting across from her turned to her manager, who was sitting next to her, her male manager, and asked her manager, is she right? And people may not realize when you say something like that you're completely, shutting down her voice because you're looking for a male leader to corroborate or to validate what she just said, rather than just trust that what she said is actually true and it comes from a place of subject matter expertise. So how do we counter this kind of bias? Is to amplify women's voices by redirecting conversations back to her. In this situation, my colleague said the right thing that her manager did was to just point back to her and say, whatever she said, she's a subject matter expert, she knows more than I do. And that way he pushed the meeting back to her, he gave her back her voice, and he was able to provide the support to her by doing just that. He could have repeated what she said, which would have also been helpful, but it generally is seen as you're actually doing maybe what is called as mansplaining, because you're saying it in your words as a male rather than letting the woman have her voice. And so that's just one example of how we can all help through allyship and by raising awareness of these issues. The next example I have is that women don't get as much constructive feedback as men. And even though people want to provide feedback, it seems like male managers don't want to provide feedback to women because they're worried that women may get emotional or they may not be open to feedback. How do we counter this? The way to counter this is to keep in mind that everybody needs constructive feedback. Everybody needs to grow and learn. If you don't tell them what it is that they didn't do well or they could do better, how are they going to improve? How are they going to grow their careers? And so it takes courage to provide constructive feedback, whether you're providing that feedback to men or women, and to try and treat everybody fairly and understand that that feedback is really, really important. So that's my reminder, is please, make sure that you're always providing feedback. It's always welcome. Feedback is welcome as long as it's constructive, and we don't have to worry about people getting emotional. The next example I'd like to provide is, I've heard people talk about, oh, I don't think she's technical, especially in a software world. We hear this a lot where women are just assumed not to be technical, even though we have the same degrees, we have the same education, we have the same kind of experience, we are smart and competent, but we have to prove ourselves almost on a daily basis. And we do it. We do it with a smile. We do it with a positive attitude, and it helps. But it would be a lot easier if people just assumed that you're just as smart as the next man next to you. The example that I have here is when I was at around a mid-level career at Microsoft as a program manager, I was running a project, large project across multiple teams, and I was partnering with somebody from another team. And he kept coming to me and saying, well, my manager doesn't trust that you're running this program the right way. He doesn't think that you know what you're doing. And I asked for examples of what I had done wrong. I got no information, no data. And so I went to talk to my own manager about, here's a challenge. What am I supposed to do? And I went in thinking that he would support me and help me. I was expecting that my manager would go and talk to this other manager and advocate for me and tell him that she's doing a great job. Don't worry about it. But my manager did something very unique to me that was even more helpful. And he said, Keerti, why don't you just go have a one-on-one with this other person? Just talk to him about what you're doing, how you're doing it. I think he just needs one meeting with you and everything will be fine. So I was skeptical about this approach, but because I knew what I was doing, I knew everything was going well, the project was going well, I went and scheduled a meeting with him and went to talk to this person. And then he had a few questions with me about how are you handling this challenge? How are you handling this risk? And I gave him all the data points that I had. And I just told him that this is how I'm running the project. And it seemed to be enough because after that meeting, never heard any concerns back from that person again. Project was very successful and I was successful. I also had the additional positive thing here of feeling like I had gone and solved the problem on my own with my manager's support and advocacy from behind. And it was very different, but it was an amazing way to build my confidence in myself, as well as show and be visible across my team members that I was definitely on top of what I was doing. And so if you come across this in your career, or you see somebody saying something like this, you hear someone say this, my advice, my suggestion, my guidance is to be fair. That even if she's a woman, she earned her place here. Everybody goes through the same interview techniques. The same bar exists for everybody joining corporate world, like at Microsoft. And you don't make women have to prove themselves on a daily basis. Just assume that they're smart, they're technical, they're competent, and they're going to do a great job. And they do. My last example here is, something that many people may relate to, where, someone comes back from maternity leave and wants to continue their career. And you might hear someone saying, oh, she's got a new baby. Can she handle the load? Maybe we shouldn't give her a hard project. Maybe we give her an easy project, or maybe we give her something that's not too challenging. And my ask here is don't make those assumptions. When I came back after having my children back into the workforce, I had immense support from my husband. He would handle whatever needed to be handled. If I could not be back home by 3:30, 4 o'clock to pick up the children, my husband picked them up. He brought them home. He cooked for them if there wasn't enough food in the fridge for them. He took care of their needs. By the time I came home by 6 o'clock, the children were, well fed. They were doing their homework, or they were being bathed, and everything was great. So I had an amazing support system at home. And I would assume that many women who come back into the workforce after having their children have similar support systems. It may be their husbands supporting them. It may be parents at home supporting. They may have help at home. So as managers, we should not assume that maybe they don't have the time or they can't handle these challenges. And the best thing to do is ask and give them the choice. And I've had a woman join my team recently as a manager, reporting up to me. And I had a conversation with her and I said, look, I understand that you have a very little baby and you might have different challenges, different demands, but I'm going to give you the same kind of work that I'm giving everybody else on the team. And I expect you to come back to me and let me know if you think you need, some flexibility or some accommodations, or you just, you feel like it's too much for you to handle. If you come back to me, I will definitely provide you all the support. She talked about how important that conversation was for her, because it made a big difference to how she felt about coming back into the workforce, that she had the support of her manager. And so I thought these examples are hopefully very helpful for all of you listening in terms of how we can be allies, how we can have senior managers be very, very supportive of women in the workforce. There's been a lot of progress in the technology industry in the last 20 years, but we still have a ways to go. But it's very, very promising, very fulfilling that people like us can come in and we can manage our careers, we can manage our jobs, we can provide support and advocacy and mentoring to other women. And someone like me can run a male allies community at a place like Microsoft, where I have VPs and senior male leaders, where I can actually teach them, coach them on what women's challenges are and how best they can support women. We provide one-on-one mentoring to these male leaders in terms of it might be a junior woman or a mid-level woman or somebody with a lot of experience like myself, who will actually work with them one-on-one and work through their challenges on how can they help women be more successful. So this is the end of my topic today. I'd like to stop here and turn it over in case there are any questions.
Hello. Thank you, Keerti, for a wonderful talk. The talk is open for questions, any short questions, inquiries. Anybody wants to ask? Yeah, please.
Hi, this is Anuradha Ganesh and Keerti. It was a great presentation. I really enjoyed and I was able to connect also on the same. Having said that, you did give one very good example and you said that, you know, we shouldn't assume or they shouldn't assume that the women don't have help, they have. But in most of the cases, still in India, we do not have that support. So how do you suggest we handle that? Because I don't think the number of people who have that kind of support is still increasing. It's stagnant.
Thank you. That's a very good point that you bring up. And for those who don't have the help, don't have the support, there are many options, right? And the assumption has to be, when the woman is coming back into the workforce, that she wants to be back in the workforce and that she feels like she can make it work. And so in that case, if she doesn't have all the support in the house, then it's even more important for her manager to provide her the flexibility. Maybe there are certain hours that she is not able to work, and to help her by protecting those hours. I've had people on my team who've come in and said, I have to do childcare from 3 to 6 in the afternoons and I'm not available. And I have completely supported them on that, because when somebody tries to schedule a meeting between those hours, I have gone to them and said, this person has asked for this flexible time and you'll have to schedule your meeting at some other time. And I, as her manager, I'm completely supporting that. So unfortunately, you're right that it may not be the case that everybody has the same support. I think in the workforce, we can provide even more support. The other point I will add, because this is such a great question that you have asked, is a lot of women feel guilty about coming back into the workforce. And they may not have the emotional support around them where people make it okay for them to go back to the workforce. You might have family members who are, trying to say, oh, your baby is so little. Why are you going back to work? Why is it so important? Is it about the money? It's not about the money. I think it's really, really important for women to be able to come back into the workforce as soon as they can. Otherwise, they risk, not coming back into the workforce. The longer you leave it, you get obsolete, you lose your skills. And so it's really important. And so the ask is out there for family members, please support women coming back into the workforce. It's a temporary thing. They may have given birth, but raising children is a community thing. And so the ask is for partners, for family members, all of you to pitch in and provide equal support.
Very well said. Thank you so much. Thank you.
Dr. Keerti, thank you very much for an interesting talk. My name is Bahukutumbi, a good friend of another Mahajan in the setup. I was wondering, the latest news item that I read about support to working women is an address by Oprah Winfrey, the TV anchor, the person who carries out TV shows in New York, everywhere else on American channels, and Michelle Obama. And both of them were pleading about facilities for women in menopausal stage. Have you heard about that? What is your reaction to that?
I have, and thank you so much for raising that, because it's not just about, people are in the workforce in all different stages of their lives. And, we have started working in the technology industry, 30, 40 years ago. And so now there are a lot of women in that stage of their life. I have a few people who've come to me with these kind of discussions. At Microsoft, we have actually a forum where they talk about aging women and menopause and hormonal impact. And it is really brave and courageous of these women to be able to have this. I've had people come talk to me about, their managers not understanding when, a woman is going through perimenopause, she is having hot flashes. And these are things outside of your body's control, just like, having a baby, right? And so what I've heard is one woman came and talked to me about her face goes red when she's talking, and she gets very emotional and she starts crying. This is not something that would normally happen, but because of the hormonal impact, it does happen to her. And she had a bad experience because her manager didn't understand that the reason why she was getting emotional was because of the hormonal things. They thought, they gave her feedback saying, you have to be able to deal with difficult situations with more maturity. And so she felt very unsupported. And she was able to come and talk to me. I was able to talk her through, things that she could do. So you need a lot of support. But the best part is that people are talking about it. And in our male allies community, this is something that we are going to talk about, saying, let's educate you on what happens to women at these different stages in life and how men can support the women through all of these stages. And it's a temporary thing. The sad thing is it's very temporary. It's not, the rest of your life, but a lot of women actually tend to leave their jobs during this time because it's so hard to cope. And so thank you so much for raising this question. It's a very, very important topic. And my ask again of everybody in the audience here is be aware of those hormonal changes, and please support all the women around you.
Thank you, Keerti, very much. There are so many young working women in the audience here today. And I would like to just say another point, which is very heartening. There is a very popular TV channel in Hindi called Sony, and it is in Hindi. And there is a show there at 9:30 p.m. girls. Udan, not Katha, Udan, Sapno Ki Udan. And how a young girl from a small town in Uttar Pradesh, she comes to Mumbai, and the sort of prejudices which she faces with her male colleagues and how she encounters that. So it was very heartening to see this sort of show, on our very popular TV channels, which otherwise talk of only saas and bahu and things of that sort. Thank you very much. I enjoyed your lecture very much.
Thank you so much.
Yeah, I'm not young one. I'm 50 plus. Excellent presentation, Keerti. Yes, you did mention the challenges as an employee of Microsoft, and as a business owner, boss of a company, I have also faced a set of challenges. But you've probably commented on the challenges that you faced in terms of the higher ups. How do you comment on the people who are working as your subordinates and below you? How do they respond to you and take you seriously there?
This is also a very good question. Thank you for raising this. Again, it is about persevering and showing your subject matter expertise, right? When you show that you have answers, you are able to provide guidance, you're able to provide solutions. People who may have prejudices may, understand over time that you are somebody who can and support them. The other thing I find as a manager is it's very, very important to establish a trusted relationship with the people that you're working with. And so it's a journey, it's a struggle. And I will say very candidly that there are some people who their biases are so internalized and so strong that maybe they will never change their mind, right? And so if that is the case, maybe not working in that same situation might be the answer, which means they may not be working for you anymore. It means you continue to have your position, but hopefully this is not a widespread issue. It is more of a one or two people who either you can educate them, raise awareness, and build the confidence, build credibility. And if it doesn't work, then maybe it's not a good fit. So that's kind of my candid answer here.
Thank you, Keerti. That's great.
Hello, can you hear me, Keerti?
Yes, I can. Thank you.
Hello, is it okay now?
Yes, yes. Hello.
Thanks for such a lively discussion. It's really very enjoyable. And I'm happy to see that you people have overcome the challenges that we all faced. So very nice. Thank you.
Thank you. Thank you. We need the encouragement. And we also look up to all of you as role models. Thank you.
So I'm sure that there will be many more questions, and many in the audience would like to express their views, their experiences, share their experiences, but we have to stop here because we have to keep time also. Thank you very much for a very wonderful talk, and maybe sometime they will be able to contact you again. So let us move to the next talk by Dr. Umasankari. She is present here. We are very fortunate that we have a speaker here, and you can interact directly here. She will be introduced to you by Dr. Madhu now.
Thank you, ma'am. Our next speaker, Dr. K. Umasankari. She is Head Reactor Physics Design Division, BRC, India. She is a reactor physicist recognized nationally and internationally. She has designed the advanced heavy water reactor with thorium-based fuel for enhanced fuel performance and safety. Physics design of railway pressurized water design of Indian pressurized water reactor and molten salt reactors are also led by her. Thorium utilization, thorium fuel cycle, and nuclear data physics are her forte. She has significant contributions in qualifying new fuel with several experimental and irradiation programs. She has co-authored a book, Physics of Nuclear Reactors, published by Elsevier. As senior professor of HBNI, she has guided several PhD students. She has over 98 papers in peer-reviewed journals and international conferences, 132 papers in national conferences, and 6 technical articles on thorium utilization. We welcome you, Shankari. Please stand.
Thank you very much for the kind introduction, Dr. Kulkarni and Dr. Bhava. And you have put my presentation. It is an honor for me to speak at this Golden Jubilee celebrations of Indian Women Scientists Association. I have been associated with them on and off, and it's a lovely conference, and we see such beautiful, lovely talks and interesting talks, mainly by the next generation. I would call the Gen Next, and they have all come up with flying colors. So that is what is very interesting. So my topic today is a little difficult because it's not directly my field which I have worked on. I will have to showcase the talent because this session itself is technological achievements of women. So I'm trying to showcase all the achievements done over the past and as part of the nuclear energy program in India. I hope to do justice. So please bear with me if I missed out some names, or I'm not going to give any names. I'm only going to give the fields. Okay, so I would like to speak on, this is a general outline about some statistics of STEM statistics in the beginning, and the pioneers who have done some great work in the nuclear field, and a few achievements of India in the nuclear sciences and engineering, and what we should do to outreach so that we get more women participating in the nuclear industry, and of course, a few words in summary. So here you can see, it's very difficult to see the screen from here. What is the various aspects for women who are in the field of science and technology? First of all, mentors play a positive role. Then the atmosphere also plays a positive role. Family support, yeah. Yeah, that's it. Okay. The family support is probably having a 50-50 participation or in the achievements of women. And self-motivation. This is the one which you should not lose. Self-motivation is what you should make it into a top arrow, or it should govern you. So there have been so many documents which have been released by the government of India. One is Women in Science and Technology. Then you can see this. What happened? I have to go back. This is for going back. Yeah, no? पीछे नहीं जा रहा. I'm sorry, it has run. This is the cursor. Cursor. नहीं, ये पीछे जाता है. अच्छा, अच्छा. Sorry for all this inconvenience anyway. Okay, so there are a lot of I see there are a lot of documents which have been released by for the women in STEM, and there are these documents. Dr. Rohini Godbole was one of the pioneers in some of. She was in partly associated with most of these projects. And here I give you some statistics. See, how do girls fare in the fields of science, as we call it the STEM field? So you see, mostly life sciences, physics and chemistry and pharmaceutical sciences, you can find good representation. And this is the representation with respect to the arts, science, engineering, and medicine. You can see engineering is a mere 20%, even in the entry level. And you can see subject-wise distribution, which is on that here. And you can see that about, again, in the engineering field, there are much less, whereas in hello. So in the engineering field, it is much less, whereas in the medicine and science, this is much higher. So this is all just some statistics you can find in, of course, this was done in the year 2000 and 2001. And what subjects exactly do, this again was a survey which was conducted by the All India Survey of Higher Education in 2016 and 17. You can see that in BSc level, there are about 50% of women. Whereas in BTech, it's only about 20%. And again, MSc, it's more than about 50 to 60%. And PhD in chemistry, and these are all subject-wise. So what it sees is medicine, biology is well represented by women. BTech, engineering, PhD are all, of course, inviting you for an exciting engagement with the STEM subjects and then a professional career as well. But look at mathematics. There are 50 to 60% women who have taken up mathematics in the highest scale, like PhD in mathematics. But where are them? Do you see those mathematicians here? You don't see them. We only saw one Nina Gupta yesterday. So where are these 50% of mathematicians? So this is what we have to stop on down. Again, there is some statistics from India with respect to the other countries. In India, 42% of the women take up higher education, which is not very different from other countries. And here you can see about the situation is pretty much same in every country. I have UK, United States are all at 33%, 38%, and so on. And this is continuously taken for about 3 years, 2016, 17, and 18. So now where are these 40% of the women who do? Only 20% land up in national labs or industry. So why is that? So that is what we have to study and how that is what we have to do. Now I come to my field of nuclear energy and sciences. It's a highly technical, technology intensive and engaging field. It's multidisciplinary in nature. You can see that a lot of related fields which are shown there. Several levels of expertise is required. And there is a specialized training which is required, which we do at the Department of Atomic Energy. And of course, it's rocket science. Now I would call it nuclear science. Rocket science is generally a class of known for all these difficult kind of sciences. So nuclear, so anything and everything with atoms, its constituents, its manifestation. So it's a very, very large technology encompassing several fields. Now, I would not be doing justice if I don't start with the pioneers because of whom we are in this field. So these have been my role models, and I have been amazed by their achievements. So of course, you know, Marie Curie, so the discovery of radioactivity, and Lise Meitner, she's a physicist who explained the process of fission. So I'm very much in awe of her. And they all had come up in very, very difficult situations at the time when women were not really given their due, and these people are really should have got the Nobel Prize, but of course they have not got. And this Catherine Way, she's established a nuclear data project. We call it a Way-Wigner formula for calculating the beta decay rates of fission products. So whenever you go to Google, you see the 5 most influential or women of nuclear energy, you will get these 5 names. Then Cheng-Shi Wu, she's also a particle physicist. She designed and carried out the famous Wu experiment on beta decay with the radioactive atom cobalt-60, and she precisely measured the small particles released from the atom. Then we have our own Vibha Chaudhary. She was a cosmic ray physicist. She worked in the polar gold fields with energetic muons, and she had studied the cracks in the cloud chambers. And of course, they also say that she also missed the Nobel Prize, or she was not recognized when she didn't get her due. She was associated with TFR. And there's Liana Woods, who was the youngest person and the only woman in the team who's responsible for the world's first nuclear chain reaction, which was at the Chicago pile. And there, at that particular time, you can see Vibha Chaudhary in a conference in Pisa, Italy. And then here on the right, I'm showing you Marie Curie in her lab. So of course, these are all pictures from Google. Now let us talk about today's women in the nuclear domain. I have given 2 examples of which I could able to collect from VRC and from IGCAR. We are about 22, even the UN statistics says that it's about 22% of the workforce in the nuclear sector is occupied by women. And in VRC, we are about scientific and technical staff put together about 1,500 women who constitute about 23%, whereas in IGCAR it's about 12%. But in HBNI, which is the institute which is responsible for the higher education, which is PhDs, they have given me a statistic that 50% of the students are girl students, which is a good sign. Now, the distribution of women in the technical category, you can see this is a kind of distribution, and this whole thing is basically the scientific cadre where we join after our post-graduation or BTech degree. And you can see that there is a minuscule percent representation in the leadership positions, which is only about 5 as of today. It was a little higher earlier. So today is 20%. Can it become tomorrow 80%? That is what we have to think. Or at least we should target of 50% in the next decade or so. And also we should say that women in leadership positions should increase. There is an increase now, but we should see how much more we can participate in the decision-making bodies. Now I come to some specific technical achievements. And I would start with my field first because nuclear reactor design. There have been a lot of achievements with respect to the Dhruva reactor design, the Thoria bundle design for PSWR, and thorium utilization, even in the back-end analysis of the fuel cycle, that is the reprocessing, the light water reactor design, cross-section data. The neutron cross-section data is still today not available. It's a cutting-edge technology, and we'll have to go elsewhere for getting these cross-section measurements. And these are some of the achievements. There's a ASWR cutaway view I'm showing. There's a Kamini reactor, which is the first reactor which used thorium, which has been done by many of women are associated in most of these, almost all the bullets which I have shown here. I'm only showing the field here. And here you can see this is one of the solution which is given by one of my predecessors, again a lady, Dr. Kamala Balakrishnan, and she has given this solution where we didn't have we had a uranium crunch, and this with use of thorium bundle was used in about 6 reactors in the operating pressurized heavy water reactors. To redesign something in an operating reactor is very, very difficult, and this was successfully achieved. And so I would like to showcase one of these achievements because it's an achievement of a woman. And of course, this is my own book, which I'm showing here, and the thorium utilization part, and I have been involved in optimizing the fuel cluster design for Indian pressurized water reactor, which is an enriched uranium-based reactor. Coming to the fuel cycle, I know I thought Dr. Shashwati Roy would be here. At the front end of the fuel cycle, that is the fuel fabrication. Women are involved at every stage, right from uranium metal extraction to chemical processing to uranium enrichment, specification, and particle, that is a small tiny particles which you can see here. So you have a rod type design which is here, and there's a tiny particle size which is like a rye seed, and there are 3 layers in the rye seed, and there's a uranium pellet. So the women are involved in many of these processes, right from the fabrication at plant level to the design at their in their workstations. Or women contribute significantly in all these fields. And the back end of the fuel cycle, which is called the reprocessing, we are working on the spent fuel reprocessing, criticality simulations, actinide separation. We separated in India. We believe in reprocessing or using everything what is being produced in the reactor, and which is what we get plutonium and also the fission gases. And this is a flow chart of the back end of the fuel cycle, where how the fuel goes into the reactor. It is producing energy. It comes out of the reactor. You extract the useful products out of it, and it goes back again into the reactor. And you require microstructure evaluation of the fuel, which is also being done. And this is a typical fuel. And going still deeper into the thing, or you can do the molecular dynamic simulations of the fuel. And this example which is done for a typical lithium fluoride, thorium fluoride fuel, which is being used in molten salt reactors. Dr. Bharadwaj was very much involved in all these things. So isotope separation, you name it, all the fields, everywhere women are involved. And this is again radiological physics, another important aspect of nuclear energy generation. So there is women who are working on the Gaussian plume model, how the radiation transport is happening outside the reactor, inside the reactor, what kind of optimization is required to contain the radiation. And of course, today's we work on the linear no threshold theory of cancer deaths, women are involved in establishing or re-establishing this theory and seeing whether it's be linear or non-linear or how it should be. And there is a radiation zone mapping required, environmental mapping. Women lead in the radiological protection and nuclear instrumentation in research labs and industry in the Department of Atomic Energy. Then I thought Meera would be here and I'm speaking about radiopharmaceuticals and radioisotope production, but she has been a doyen in this field and a lot of work which has been done on the radioisotope generation reactors and also with respect to the neutron activation, specific irradiation in reactors and in accelerators, and radioactive ion beams using both cyclotrons and proton beams, ionization studies, radioisotope generators. Now today we are working on fission moly production, which is the plant has already started producing, which is recently commissioned. With respect to food preservation and isotope hydrology, the use of radioisotopes for peaceful applications or other applications, non-power applications, that has been enormous. So you can see that Dr. Sudha Rao is also here. She was also participating in all this food preservation. Gamma irradiation. Now today we have a cargo scanner for even for the being designed for the ports. And nuclear medicine, it's a huge field in itself, and there are a lot of people who have been working on it. And here I have shown a gamma irradiator. This is a leak detection using radioisotopes. So these are other uses of radioisotopes where women have significant contributions. And with respect to nuclear security, operation, and regulation, I have shown a picture from the internet where a young girl from NPC is in front of a control room. She is in the control room. She is a control engineer probably. And operation of nuclear power plants, all power plants, whether it's research reactors or whether it's power reactors, whether it's accelerator systems or fusion systems, women have been doing even the round-the-clock shifts, and women have been in definite operations of these reactors. And regulation and other specific fields are nuclear economics, nuclear forensics, nuclear security, nuclear journalism. You would find women in significant roles in all of these. So they can take up any challenging task and work at par with men, as I told you, even in the round-the-clock shifts, in all nuclear plant sites and all other laboratories. And I'm sorry, I could not get much of data from my engineering sciences because I had to, it would be a huge talk otherwise. So the control and instrumentation aspects of every reactor, there have been pioneering efforts which have been done by women. Then the development of neutron detectors, the fission detectors, and the solid state detectors. Here I'm giving you an example of a crystal growth of a sodium iodide detector. And this is a Bhabatron, which is again of nuclear medicine for therapy and for diagnosis using a cobalt-60 machine. And there's remotization, automation, high voltage engineering, power electronics, reactor simulators, everywhere you can find women. And this CMS, what Dr. Archana was talking yesterday, a set of detectors have gone from BRC, which have been designed by a women, and it has been incorporated into the CMS project in CERN. And this is a mimic of a reactor. BRC has delivered about 1,100 detector modules for the CMS pre-Shiva. So these are some of the significant achievements. Now we can go on and on about so many things, but I would just like to say that in science, women lead, of course, in all these fields of nuclear technology, but in science, the leadership alone is not important. Your research is your leadership. So if you do good research, that will be driving you, and curiosity should drive you. And in mega projects, there should be teamwork. Yeah, you can see this lady who is helping her teammates both ways, this way and that way. So that is how a leader or a team leader or a woman leader in leadership position should be. And one word about the publication of women scientists. There's a scientometric data which was done for a period of about 5 years from 2006 to 2010. About 1450, this again only BRC as an example, about 5,290 publications in journals. 1,450 of them were by at least one author as a lady or a BRC woman scientist. And average contributing women authors were about 36% out of 5,762 where both men and women were contributing authors. And highest number of publications were in the physical sciences, followed by chemical sciences and biological sciences and so on. Collaborative analysis indicated that 69% were intra-BRC, 17% national, and 12% is international collaborations. So based on this critical analysis, it was found that 634 women scientists, which is about 16% of the total number of scientists, they contribute to about 36% of the technical journal publications. So you can see even 16% of the women are contributing 36% to science. So which means you just imagine if 50% of that we would like how much of publications which we would be able to do. This I've taken from the paper here. Of course, what we should do is what like IFSA or I represent as a chairperson of the Women in Nuclear in India, which is a very an organization which was just formed last year. So we should be spread awareness on the benefits of nuclear energy at several levels of outreach. Like IFSA is doing with school children and with college children and with the professionals. And there is INS and there is ISRT. There are so many organizations and the international bodies like IAEA and CERN. And what we should do is seminars, publications, news articles, popular science articles. Many of these initiatives are already taken by IFSA. And media and contact with schools, colleges, mentoring. That is what is very, very important. Internships, projects, etc., etc. And in summary, I would say that women have significantly contributed in the nuclear field. Individual contributions are on the increase. They lead many programs. They encourage colleagues, and we should make more social support systems and prioritize our work. Individually contributed and worked effectively in the team. Several new schemes for women are there. For young women have been there. I was recently invited by the PSA to formulate policies for empowering youth in sciences. And women can be good ambassadors. They can spread awareness about the benefits of nuclear energy. And with this, this is my last slide. I would like to have two quotes, one by Marie Curie. She says that nothing in life is to be feared. It is only to be understood. Now is the time to understand more so that we may fear less. So women, because you are soaring on the wings of change. And of course, we have minds to go. There's another quote by Swami Vivekananda which I would like to quote. It says, there is no chance of welfare in the world unless the condition of women is improved.